Hello, welcome everyone. Today we'll do analysis for a dam. The dam will be a very simple one as shown in this figure. The gray portion is the dam, which will be height of 50 meter and width of 10 meter, and we'll apply loading as shown in this figure. We'll apply load in a step. In the first step, load will be up to 5 meter, and in the final step it will be up to the top of dam, and in between we'll increment the load in 5-meter steps. Currently we'll only use the hydrostatic force, that is the depth multiplied by 9810. In this tutorial we'll do the analysis in two parts. The first part will be the direct application of whole force, and in the second part we'll read the function file from external file and apply it in code Aster. I'll start first by creating the function file, but we'll use this file in the later portion of this analysis. Okay, let's get started. First I will open Excel file. In Excel we'll need a format as shown here. First, on the top part we'll need the time instant, and in the lower part we'll need the variation of pressure with depth. I'm just copying from the previous part. The Z will be as shown with the increment of 5 meter. I am first calculating for the last step so that it will be easy to copy. It's just the height multiplied by the pressure force 9810. And then for other time steps I will just make copy of the last time step, but with a decrement of one step as shown here. Just a copy paste procedure. Note that we'll only be doing hydrostatic analysis right now. The point is to show you how to do it. The forces on the other part will be 0 as shown here. We need to copy everything from Excel to a text file, and we'll save it as input file in our hard disk. And note that we'll use this file in the later part, not in the first part. In the first part we will only do a simple analysis and then modify it to include this file. I hope you will understand what I am doing here. It's just time instant on the top part and the pressure forces on the lower part, which varies with depth. Now let's go to the code Aster. Let's begin by making a new file. In geometry part it's very simple. I intentionally choose a simple geometry so that we don't have to waste time here. You can make your own complicated geometry of dams you like. Here I'll make solid box with the dimension as shown. Once the box is created, we make the groups. Let's make a group for volume. Let's call it dam. For that we need to select the shape first and then add it in the group. Next we have to make group for loading and for support. For that we first let's a bit rotate the view to see the loading phase. I'll apply load in this phase and name it as loading phase. Let's apply it. Similarly, let's make the support phase. Support phase will be on the bottom part. Note that Z coordinate will be 0 at the support phase and will be 50 meter at the top phase. Once we are done with geometry, we have to go to mesh module as usual. And let's make the mesh and create mesh. Let's select the geometry. We'll use simple NetGen 1D, 2D, 3D in this case with some simple parameters. I'll choose the maximum size of element to be 5 meter and minimum to be 1 meter. Okay, let's apply it. Now we have to compute the mesh. Once it is done, we have to make the group as well. We have to create a group from the geometry. And to calculate reaction, I will need group of nodes in the loading phase. Sorry, not support phase. Yeah, let's choose the support phase and apply and close. To make it simple, I will rename the support phase as support nodes. And that's all we need in the geometry and meshing part. Let's save it. For convenience, I will export the mesh. I think it's good habit to export the mesh file once you created it. Now that's all. We will go to the Aster module now. In Aster module, we'll first make the simple analysis, which is a mechanical linear analysis, but we'll use mechanical non-linear, but the setting will be for all linear analysis. Let's add the stage and let's read the mesh. Let's assign the finite element. We'll use phenomena of mechanic with 3D as model. Yeah. Once that is done, let's define material. As I told, we'll only be doing linear static analysis, so we'll use only Young modulus and Poisson ratio. For dead dot calculation, we will use density. Once it is defined, let's apply it to the model. Now we have to define function. This function will vary with depth. That is, we are going to apply a triangular load from top to bottom. As I said in the first part, we'll just make the model applying force from top to bottom. We'll not use the variation right now. We'll keep the variation in the second part. You may understand at 50 meter there will be 0, and at the bottom of Z value at 0, pressure will be maximum. I gave it the name press fun standing for function. Next, we'll define the boundary conditions. First, let's use boundary condition for support. For that, we'll fix the support face. I'll rename it as fix. Now let's define the load itself. Notice that I used afe kara mecha f to f standing for function, and we'll apply to the loading phase the function press fun, which varies with Z. Let me also define boundary condition for the dead load. Just name it as dead. It will be a gravitational force. The gravitational coefficient is 9.81, and the direction will be Z on the third part. Once that is done, we need to define time step for nonlinear analysis. Actually, we are using nonlinear analysis only to discretize the analysis in time for the second step. In the first step, actually we could have done just a linear static analysis. Once that is done, let's define nonlinear analysis. Let's input the loads. And all the boundary conditions. Time step will be this one. Just now we defined. Note that it has 10 time steps from starting from 0 to 9. That's all. We have to write this result to the output file. Generally, I prefer to output in MET format and Aster format. MET format helps for graphical visualization, whereas result format helps to visualize in text file. I mean, you can get all the numbers. To calculate reaction, we have to do post-processing. I'll name it as reaction, and we have to calculate the forces called reaction node. Note that the static nonlinear file only has displacement and stress values. Once you calculate reaction, we can also extract the required values in a table with the post relativity. We'll select the group of nodes. It may not be visible, so you have to go back to the mesh module just to know the name. I'll just copy the name group support nodes and just paste it in the Aster module. Here we'll calculate the reaction only in x direction. We'll name it as reaction forces. Num_champ is reaction node that we had calculated, and operation is extraction. Extraction means it will sum up all the reaction force of the nodes and give it in our table. That's all. And we have to write the table in a text file. Let's name the table as reaction table. It's just a text file, you can give any name. Now let's do the analysis. Oh, there is something wrong. Let me see. Okay, there is something wrong with CalChamp. Yeah, we should have taken the reaction instead of the resultant file. Let's save it and let's rerun it. Everything is okay. Let's go and check the output file. Yeah, here is the reaction forces. You can see the reaction in x direction, and it is constant all over the time step. This is because we didn't vary the load according to time step. I'll show you how to input now variation of load with time step. The Excel file on your left shows the time step on the first part, and this will be represented as norm para inst in Lyrae function. Okay, you can see in the top the function name is Lyrae function. Lyrae means read the function, and the first part, the yellow part, will be the first block to be read, and the column will be first column. So time step will be read from first block, first column, so 1 comma 1. And for each time step we have to input the variation of pressure forces, and this is the green part, and this is second block in the file to be read. So first column of second block is the variation of Z, that is indices abscissa is 2 comma 1. Second block, first column. So norm para is Z, so it is varying with Z, so name norm para function is Z. And for defi function part, we'll read the variation of pressure with Z according to this format, that is second block, second column, second block, third column, and so on for each time step. So what I mean is, for time step of, let's say, the first one, the P1 column will be active. For the second time step, that is time step 1, the third column will be active, and so on. For the last one, 9th time step, the last column will be active. So this should be everywhere. This should match everywhere. Each time step should be matched. Now let's go to code Aster and read the external file. This is Lyrae function. The parameter name is time, because first we need to know how Z varies with time. And another thing is we will read it as a nappe. Nappe means a tablecloth. Is a 2x2 function. Indic para and norm para are related. So time step will be read in the first block, first column. And when this time step is read, for each time step, we will read the function. This is not interpolate function. What I want to do is first define how the interpolation will be done. It will be linear. And for Diffie function part, we'll write for each time step the required value. Those the first one is second block, second column. So 2 comma 2. Similarly for time step of 1 and so on, we'll define the varying z function. I'll just fill up it. Second block, fourth column, and so on. Last one will be second block, 11th column, because in the first column there was value of z. Yeah, the first column is value of z. So numpara function was z. It was in the second block, first column. Yeah, that's all we have to do. Just for my own confidence, I will check if I have done it correctly with the text file that I had created previously. Let me check. Yeah, the first part is indexrisu. Format is libri. Libri means free format. Yeah, everything seems okay. So I'll save it. Next thing is I have to change the function name to press. It is also for convenience only. Now the press font that we defined earlier will be useless now, so we have to change the boundary condition. Press rep to press 2, the one we defined just now. Actually we could have deleted press font, but for now let's keep it is as it is. I think that's all. Note that we only modified the function. Now let's run it. Everything is fine. Screen. Because I am running in Windows, I have to check message file as well. Seems everything is okay. Let's open the file, output file. You can see now dx has changed. Let's copy it into Excel file. Note that the pressure has varied with depth. Also the reaction also varies with the depth. For time step 0, actually the resultant is maybe due to dead weight only. It is not so much relevant. But anyway, let's calculate. For time step of 0, height will be 0. And for time step of 90, height will be 45 meters. Let's draw it in a graph. There are so many unnecessary graphs. Let's delete all of them and only input the required one. In x direction I will put height, in y direction I will put the reaction. This is the almost force displacement kind of relationship. Since this is a pressure varying with depth, the square of height should be linearly related to the reaction. I did something wrong, I guess. It should have changed. It should be squared, not this multiplication, squared. You can see that now normally more or less the reaction is almost linear. To check the value, as our dam was 30 meter width and the pressure force and the square of height divided by 2 should give us the reaction for the last step. You can see these two values are equal. I mean, they are opposite in direction, but they are equal. Yeah, this concludes this tutorial. I think I took a bit long time to describe the tutorial. If there is any confusion, please let me know. Thank you.